Hello, Percy. This is the derivation of the energy balance for non-isothermal reactor design. Applied to the control volume on screen, in symbolic form, the energy balance is written in the following form. In words, it is the rate of heat flow into the system from the surroundings minus the rate of work done by the system on the surroundings, plus the rate of energy added to the system by mass flow into the system, minus the rate of energy leaving the system by mass flow out of the system, which equals the rate of accumulation of energy within the system. The work term comprises the flow work done by mass entering and leaving the system and the shaft work done on the system. Equation 2 is now subbed into equation 1 to yield the following results. We know that the energy of the mass entering and leaving the system is made up of the internal energy, kinetic energy, and potential energy. Assuming the kinetic, potential, and other energy terms are negligible in comparison to the enthalpy, heat transfer, and work terms, then the energy of the mass entering and leaving the system is equal to its internal energy. Further, we know that enthalpy is the sum of the internal energy and the flow work, and multiplied with the flow rate, as in the energy balance. This equation is then subbed into the energy balance to rewrite it in the following form. Here we write the general equation of A plus B to C plus D per mole of A. And now, expanding the summation terms in the previous equation, the entering flow rates are related to the entering flow rate of A by theta, while the exiting flow rates are also written in terms of conversion. This procedure is repeated for all the species to yield the following table. Next, the subtraction terms in the energy balance is evaluated. The sum of the flow rate times the enthalpy of the outgoing material is subtracted from the sum of the enthalpy times the flow rate of the incoming material. The terms containing the entering flow rate of A are grouped together, while the terms containing if the incoming flow rate of A times the conversion also grouped together, as done in the following manner. We now define the heat of reaction in the following manner. We can also see that this term is stated directly in the previous calculation. Substituting the above two equations into the general energy balance, we are left with the following result. The enthalpy terms in the energy balance can be related to the Cp value. If we assume that no phase changes occur inside the reactor during the chemical reaction, the enthalpy of formation at the reference temperature and the enthalpy of species I at temperature T, the temperature of the reaction, is related by the following equation. We then calculate the change in enthalpy when the reacting fluid is heated without phase change from the entrance temperature to the temperature T inside the reactor in the following way. If we substitute this result back into the energy balance, we obtain the following equation, which is the energy balance for the design of a non-isothermal reactor, and also the desired equation.